Hello again. This is the second part of lecture 8.1. We're going to continue on. We've looked at what density, pressure, and relative density specific gravity were. Now we're going to look at how those apply to fluids and discuss pressure in fluids. So back to our slideshow. We'll go to slide 19, I think, which is numbered 18 because the slides start on 0 for the title slide, if that's been confusing anyone. Fluids and pressure. So when we had a solid object sitting on another solid object, we talked about pressure between the two objects, one of them pressing down on the other. Pressing down, that's a pressure. Fluids are a little more complicated though, because fluids can flow around. They're not confined to one static shape like we have with a solid. So while there'll still be pressure on the bottom of the container that the fluid is in, just like if you sit a solid on top of something else, what we'll also have is this pressure on the sides, because the sides of the container are keeping the fluid in that shape. If the sides weren't there, the fluid would flow down and it would just spread out really thin on the ground or surface. So those sides are actually being forced, they're forcing the liquid up into the container. They're holding it in place. And that means that there's going to be a pressure on those as well. We're going to talk a little bit more about this later on, but just thinking about that now might help you conceptually with some of these discussions. And in gases, of course, liquids, when we're talking about liquids, it's just the sides and the bottom, but in a gas, we've got the top as well, because the gas molecules, remember, are flying around in every direction. So the gas is not only pushing on the bottom and the sides now, but it's also pushing on the top. So the fluids will always have pressure on the side and bottom. Gases will have it on the top as well. It's very useful to understand where the pressure comes from. So remembering that pressure is a force over an area, and remembering that fluids are made of molecules or atoms flying around, particles flying around, whether it's within the liquid flowing or in the gas actually traveling, just flying in every direction. They are particles and they are traveling around. When they hit the wall of the container, then they will bounce off the container back into the fluid. And that means that they've had a change in momentum, which means they've experienced an impulse. And an impulse, of course, requires a force. So that means, by Newton's third law, the force is applying the wall is applying a force to the particle, and the particle is applying a force to the wall. So therefore, the wall has experienced this constant force. All these little impacts from all the particles will appear to be on the larger scale, because we can't see each individual impact. We just see the net effect. And the net effect is that there's just this constant force on the wall of the container. And that is where the pressure is actually coming from. It's coming from all of the collisions of all of the little particles that make up the fluid within that container. So that's what pressure from a fluid is. But pressure within a fluid can be a little bit trickier. So we'll often talk about different scenarios, and we'll sort of slip between the pressure from a fluid onto the container versus the pressure in a fluid without really discussing the distinction. And indeed, there isn't that much of one, because the pressure in a fluid is the same everywhere, as we'll see soon. But it is useful to realize that we can mean different things. So we can mean the pressure of the fluid onto the container that's supporting it, or we might mean the pressure within the fluid, so that if you imagine putting an object into the fluid, all the particles would be hitting that because it's now in the middle of the fluid and it's trying to flow through where that object is. So the object would experience force from all those collisions, and so it would experience a pressure due to being submerged in that fluid. So we've got pressure everywhere in a fluid. Right? We can only measure it if we go and put a device there, but it's always there everywhere in the fluid, because particles are always moving and always colliding with each other and with the container. As a little aside, we've got atmospheric pressure. You've all heard the term atmospheric pressure. Hopefully you've met it previously in your studies. We live in a fluid. Air is a fluid, so we are living constantly in a fluid. And just like I said, when we submerge something into that fluid, the particles are hitting it from all directions, and so it's subjected to a force from all of those, which is a pressure, because we've got an area of the object. And we are just like that. We are subjected to this atmospheric pressure. Because atmospheric pressure is so constant, right? It's everywhere, all around the world, all the time. It does vary by altitude, but it is relatively consistent to a certain amount of precision at sea level around the world. We do have a use for defining atmospheric pressure as its own unit, rather than saying atmospheric pressure is 101 kilopascal. It can be useful in some scenarios to just say 1 atmosphere of pressure, 1 ATM, 1 atmosphere of pressure. So officially that's defined as 101 kilopascal. There are other pressure units that you may encounter, especially when dealing with atmospheric pressures, and those are the bar, which is 1 times 10 to the 5 Pascal. So kilopascal being 10 to the 3, 1 times 10 to the 5 is still 1 atmosphere, but it's now just written in scientific notation. So 1 times 10 to the 5, 10 to the 5 becomes bar, and obviously 1 atmosphere in that case would be 1.01 bar. So there are different ways to write these units. Whatever you're most comfortable with is fine, but just being aware of them will allow you to interpret and understand any problems. Now suppose we've got a tub of water or fluid, any fluid, or liquid in this case, and it's static, so it's just sitting there. Well, actually it's not static yet in this problem, we've just got a tub of fluid. And if we look at the pressure at the bottom, and we find that pressure 1 is different from pressure 2, if we just take a pressure reading at the left-hand side and the right-hand side and we find they're different, then that means that we could draw an imaginary line or plane through the middle of our tub, and the pressure on one side would be different from the pressure on the other. And because pressure is a force over an area, if that line through the tub has the same area either side, because it's the same, the tub's consistent, that would mean that we have a greater force on one side than the other, and that imaginary plane would move. Of course, that imaginary plane is actually the fluid in between. And so what happens is that if the pressure is different at points 1 and 2 on this diagram, we would get fluid flow. It would flow from the high pressure side to the low pressure side. So that's what would happen if we had different pressures. Therefore, if the fluid isn't flowing, if we have a static fluid, so you just have a tub of water that's sitting there stationary, we'll talk about motion of particles within the fluid later, but overall there's no net flow of the fluid, then that means that we call it static, and that means that the pressure at a specific depth is always the same, right? It's constant at a certain depth. The wording here, pressure at a specific depth in a continuous body of static fluid is constant. So as long as the liquid is connected to another part of that liquid, then at the same depth, those will have the same pressure. If the pressure weren't constant, as we just saw, it would flow. Now let's think about what that pressure is at a certain depth. So let's take a just standard box of fluid. So the pale blue in that diagram is the fluid. The big black box is the bounding box, and then the small one is the one that we're going to think about. That small black box sitting in the middle of the fluid. Let's think about the pressure at the bottom of that box, that little box of fluid within the actual box. So there's not a real box there, we're just imagining it. So we're imagining part of the water, part of the fluid, doesn't have to be water, part of the fluid as its own little box, and we want to know the pressure at the bottom. So the pressure is force over area, and the force on pushing down on that area A, the red area A, is due to all the fluid in that imaginary box above it. And the force is going to be equal to the weight force of that fluid in the imaginary box, and we know that weight force is mass times gravity. What we're going to do here is introduce mass as being density times volume. All right, so we all know density is mass over volume, so therefore mass is density times volume, but volume can be written as area times height. And the reason we do that is that we then can divide, we can cancel out the area. We've got area on the top from our volume and area on the bottom, so we can cancel those out, and we get that the pressure at the bottom of that box, the red square marked A, the pressure is rho gh, the density of the fluid times gravity times the depth of the fluid at that point. It doesn't actually matter how big we make that box, because the bigger we make the box, yes, we're making that red area A bigger, but we're also including an exactly proportionally larger amount of fluid above that red area A. And so it scales exactly, and we end up finding that the area is actually irrelevant. All that matters is the depth of the fluid. So do take the time, if you didn't quite follow that reasoning, take the time to work through that equation, this one on slide 24 here, work through it and make sure you understand how we get out that result, rho GH. Right, so the point you want to remember, that you want to take away, is that the pressure in a fluid depends only on the depth H. This is in an incompressible fluid. So we just said that pressure depends on depth, and we've also mentioned the idea that the pressure is going everywhere. In a fluid, it's pushing on the walls and the bottom, not just the bottom like we saw with solids. So it's pressing everywhere, and the question you might naturally ask is, what's the difference between the pressure downwards and the pressure sideways? There isn't one. Right? The pressure is the same everywhere at a certain depth. So if you go right to the bottom of your tub of water or liquid, then the pressure downwards will be exactly the same as the pressure sideways at the very bottom. Right? If you go halfway up, then the pressure anywhere throughout the water is the same everywhere, and the pressure pushing outwards at that depth will be exactly the same as well. So the pressure is in all directions, and it's the same everywhere at a certain height. A good demonstration of this is Pascal's vase, or vase, depending on how you prefer to pronounce it. And the idea here is simply that it doesn't matter how much volume of water is in each different pathway for the liquid to go upwards. All that matters is that it ends up being the same depth. And the reasoning for that is that if this was a different pressure, if the pressure depended on the volume, then you'd get a different pressure below this left-hand pathway than you would below the next pathway. And if there was a different pressure here versus here, then it would flow. It would flow from the higher pressure to the lower pressure. And so you'd get flow across the bottom. And if you get flow across the bottom, that liquid has to come from somewhere. If it was going from the left to the right, then obviously the left-hand one would have to get lower, and they would end up being at different heights. So the point is that for them to all end up at the same height, the pressure across the bottom in that shared reservoir of fluid must be the same everywhere. And so therefore the pressure does not depend on the volume, only on the depth or the height of fluid. Another result from Pascal, and we've got a picture of him here just for reference. Blaise Pascal lived in 1623 to 1662. He came up with Pascal's principle, which is a change in the pressure at one point in an enclosed incompressible fluid is transmitted undiminished to every portion of the fluid and to the walls of its container. So just to define incompressible, it means it just cannot change volume. So when we deal with incompressible fluids, we're usually dealing with liquids. Gases obviously are often compressible. So if we deal with incompressible fluids, it's generally actually just liquids. So what is this principle saying? Well, it's saying that if you have a sealed thing of liquid and you press down on that sealed container of liquid with some amount of pressure, then the pressure everywhere in the fluid increases by that amount you've applied, not just the top. The top will increase by if you're pressing directly on the top, that will increase by some amount, however much you apply, but so will all the rest of the pressures in that fluid, right? It will all increase by that same amount. So an example of this, we've got, this is an example of just pressure in general being the same throughout a static fluid. So here's a static fluid-filled tube. We've got a closed end on the short end of the J and the open end here. And we want to know the pressure at the top of the closed end. So where this grey dotted line is, what's the pressure there? And so the reasoning that we use to solve this is simply that the pressure in a joined or a continuous static body of fluid, so this is static and it's all continuous because there's a pathway from the top of the closed end all the way around to this dotted grey line, the pressure is constant at a constant depth. And so that means that where this grey dotted line is on the open end of the J has the exact same pressure as the very top of the closed end. So while we might not know the pressure here at the closed end, we do know how we can calculate this pressure here on the open side. And once we know that, we know the pressure will be exactly the same on the closed side because they're at the same height, they're the same depth. Right? So when we're talking about depth, yes, this is the top of the surface of the fluid here, right? But the only bit where it's exposed to the atmosphere is here, so the depth is relative to this bit. Right? So there, that's the depth here. So if this is 40 centimeters, and the left side, the water is sitting 100 centimeters above the base, then that means that the depth of fluid at the grey dotted line is 60 centimeters. So we can use 60 centimeters to figure out our pressure at the grey dotted line, which is the same as the pressure at the closed end. And of course, pressure is just rho GH. So we've got pressure is going to be density of water, 1,000 times rho, which, that is rho times G, which is 9.8, we all know that, times height, which is 0.6 of a meter, right? Switching into SI for our calculation. So this is the solution is just reading out what I've said. Must be the same everywhere. And there's our calculation to give us 5,880 Pascal. So that's the pressure at the grey dotted line due to this stack of water. But Pascal's principle is saying that the atmospheric pressure that's pushing down on this water increases the pressure everywhere in the water by that same amount. So if this was a vacuum up above our open-topped J, if we were out in space and it was a perfect vacuum, but still subjected to gravity, I know that's counterintuitive, but imagine there's a perfect vacuum, no air, but we've still got gravity, so the fluid sits in our J, then that would be, our pressure here would be just 5,880 because there's nothing pressing down on the top of the fluid. But when we have atmospheric pressure pushing down on the top of the fluid, that means that the pressure everywhere in the fluid increases by that same amount, by that amount of atmospheric pressure. Since atmospheric pressure is 101 kilopascal, we just add that on. So we see that that on its own, due to the water, is 6,000 Pascal. So we go 101,000 becomes 107,000 Pascal. So that would be the pressure at the grey dotted line, which would be the same as the pressure on the closed end of the tube. One thing that we'll meet often when we're dealing with pressure is how we measure pressure. And to do that, we use a pressure gauge. If we want to know the pressure of something, then we use one of these gauges. But the important thing that you need to remember whenever you use a pressure gauge is that a gauge is measuring relative pressure. It's measuring the difference in pressure between the container you're trying to measure, that you want to know about, and some reference pressure. Usually that reference pressure is the atmospheric pressure of the environment around the container. Not always, but usually. So that's a pretty good place to start if you're trying to figure it out. And that means that the pressure that you actually have inside the canister or whatever you're reading is going to be your reference pressure plus your gauge pressure. So if you have a bicycle tube, for example, that you're pumping up, and your bicycle pump reader pump gauge says that you're at some positive pressure, let's just make one up, let's say it's 50 Pascal, that's very low, let's go with 5,000 Pascal instead. So you're at 5,000 Pascal according to the gauge, but that's relative to outside the bike tire, which is atmospheric pressure. So the pressure inside the bike tire would be 106,000 Pascal instead of just 5,000. So understanding that difference between gauge pressure and actual pressure is very useful. And as I said, usually the reference pressure is atmospheric pressure, but you do want to check the scenario because it may not always be. One thing that is very common is a barometer. A barometer is a specific pressure gauge for measuring atmospheric pressure. So where I just said that gauges often use atmospheric pressure as their reference pressure, what happens when we want to measure atmospheric pressure? We can't use atmospheric to measure atmospheric, or we'll just always have a gauge reading of 0. So instead what we do is we set up a barometer which has a reference pressure of 0. So the diagram here, this little top part of our tube has a reference pressure of 0. That means there are no particles at all in there. It's a vacuum. There's nothing pushing down on this column of fluid. If there's nothing pushing down on this column of liquid, then that means that the pressure at every point down this column is only the pressure due to that height of the column. So anywhere down this column of liquid, the pressure is just due to the height of the liquid. So rho GH is the actual pressure rather than some added pressure. The outside, though, is exposed to the environment, to atmospheric pressure. And that means, oh, sorry, I hate this mouse, I should get a new one. That means that we've got atmospheric pressure pushing down out here on the outside area. And if we draw a horizontal line right through here, right, then that means that the pressure at that line inside the barometer column is going to be the same as the pressure outside. And since this is atmospheric pressure and this is rho GH, that tells us exactly what our actual atmospheric pressure is. It is going to be the 0 plus rho GH is equal to atmospheric pressure. So doing the calculations here, mercury is a common one because it's a liquid, but it's got a really high density, which is useful for balancing atmospheric pressure. So mercury has a density of 13,600 kilograms per cubic meter. And if this column, was 1 centimeter, oh yeah, so this is just 1 centimeter. If that was 1 centimeter of mercury, it would add 1,300 Pascal. So every centimeter down you go, you're going up 1,300 Pascal. So by the time you get down to balancing with the mercury that's open to the environment, you know exactly how much pressure there is based on the pressure just in this column. Right, so as I've said, the red line shows our balanced pressure, and that tells us that based on the height of this, if this was 76 centimeters tall, the atmospheric pressure would be 101 kilopascal. So by measuring the height of this column, you can determine actually what the atmospheric pressure is, which is very useful. An open tube manometer is exactly the same idea, but instead of having 0 as our reference pressure, we now have some pressure we want to measure, and we use atmospheric pressure to determine it. So it's the same reasoning, the same calculation. I'm going to leave you to go over this slide and make sure you're happy with that. It's the same reasoning as we just went over for the barometer, but now we're trying to figure out this pressure at the top rather than having it as our 0 reference one. And so now atmospheric again becomes our reference one. As I said, happens for most gauges. So take the time, read through the slide, just think about the scenario and try and confirm, agree with this formula. Make sure you're happy with that formula. So that is the end of the content for this first lecture. As I said, mostly just some definitions, trying to make sure you understand pressure and density. And now that sets us up very well to move on to a couple of more topics for this week. So there's the review, all the content there, and I will do one more short video just with a few calculations, a few examples for you to follow along and work through about how we apply some of these formulas.